Design of experiments, DOE, is a very useful process improvement methodology. Microsoft Excel has some powerful data analysis tools, which I have, successfully, used for DOE. When it comes to analyzing cause and effect, we want to know what process factors affect our outputs. Correlation and regression could give us an indication of the main factors and the extent they affect the outputs. In some cases, there may be interactions among the different factors, or the mathematical relation between factors and outputs may not be linear. In these cases, it is useful to run a systematic set of experiments to test all possible combinations of factors to relate them to the outputs. Download this Excel file from OneDrive. We want to minimize process loss, and after some brainstorming among the process specialists, we concluded that 5 factors may affect loss. Based on current factor levels, we have selected the following levels to experiment with. Full factorial designs are constructed simply counting in binary to obtain all the different combinations of 0 and 1 for all factors. In our designs, we just replace 0 with -1 to meet the balance property. See sheet designs. See sheet half fraction. With our 5 factors, to run a full factorial set of experiments, we would need 32 experiments, 2 to the power of 5. This could involve time and money, before we are sure that all factors really affect our process. Therefore, we might start with a subset of the full factorial as a detection experiment. A half fraction will involve half the number of experiments, 16. We can build a half fraction, 5-factor design, from a 4-factor full factorial. We do this by replacing the 4-factor interaction, which is very unlikely to happen, with the 5th factor, flow. We construct, therefore, the flow column, multiplying the other 4 columns. To run the experiments, you need to convert the coded values to uncoded as seen in sheet run experiments. We don't want the order in which we run the experiments affect the result, so a common practice is to randomize this order. To randomize the order in which to run the experiments, use a macro pressing Ctrl+R and then follow the order indicated in column M. In this example, we are going to use a simulator with the coded values to simulate the running of our experiments. See the experiments simulation sheet. We have added 2 additional experiments, with the values called central points, all zeros, which will correspond, in uncoded values, to the average value of the high and low levels, in each factor. We do this, to make a more robust design, without going all the way to the full 32 experiments. The simulator has provided the process loss estimation outputs, for each experiment. In the simulator, every time we press F9, a new set of experiments is run, giving, as in real life, different results. We want to be able to estimate the influence of each individual factor in the result, but also the interactions among them, so before we analyze the results we will build a column for each interaction among 2 factors. If we wanted to include 3-factor interactions, we would also add them to this matrix. See sheet detection. You obtain each interaction column just by multiplying the corresponding factor columns. Just enter the formula in the first line and replicate all the way down. Enter in Excel, data/data analysis/regression. Fill in the regression form as shown. Y is the output, loss. X is the input matrix including the 5 factors and all the interactions. And the result will be. We notice that our square root of 0.9 validates our mathematical model. The probability column of the coefficients, p, tells us which factors and interactions are significant, those below 0.05. Factors temp and press have p-values above 0.05, but their interaction, p equal to 0.02, is below, therefore we must keep them both. We run the regression again, keeping only the factors and interactions not removed. See sheet reduced model. These are the results of the reduced model. Out of the 5 original factors, which we thought could affect the output, we have confirmed that only 3 affect, pH, temp and press. Temp and press do not, significantly, affect, but their interaction does. From the coefficients column we will build the mathematical formula to estimate loss as a function of these three factors. This gives us the formula for the estimation of process loss as a function of three factors. This equation is with factors in coded values. In the reduced model sheet we add cells M17 to M21 to house the results we are looking for. M17 is the factor to multiply with the interception, so it must be 1. Cell M21 should have the product temp times press, so we input the formula, equal to M19 times M20. We will ask solver to give us the values for the yellow cells. In M23 we put the formula to calculate loss with the coefficients in column I, equal to sum product of coefficients in column I and values in column M. We now call solver to minimize this value, changing pH, temp and press, yellow cells, with the restrictions that they must be between -1 and +1. We now call solver to minimize this value in M23, changing pH, temp and press with the restrictions that they must be between -1 and +1. Solver gives us these results, the optimal values of pH, temp and press, to obtain a minimum loss of 7.64. The result is that the minimum loss of 7.64 can be obtained with pH equals 2, coded -1. Temp equals 150, coded 1. Press equals 1, coded -1. We would now run confirmation experiments to validate these optimal values. We have run 14 replications with our simulator and obtained the results in sheet confirmation. We obtain a confidence interval for the process loss between 2.21 and 7.22. We can view a graphical representation of our mathematical model to help us understand the process behavior. Entering a value for pH, we can see the loss for each press and temp combination. With the color code, we clearly identify the minimum value in dark green, 7.6, which corresponds to press equals -1 and temp equals 1 as calculated by solver. We can show the same data with a 3D representation in Excel. In spite of the curvature of this shape, the behavior of each factor is linear. The twisting of the shape is due to the interaction between pressure and temperature. We want to estimate the error we make by replacing our process behavior with this mathematical model. See sheet residuals. We subtract the actual loss values, measured in our process, from the estimates of our formula, to obtain the residuals. We see no trends of the residuals versus estimates, along the estimate range, so this is okay. The next check is to make sure that the average of the residuals is close to 0. Also that the residuals follow a normal distribution, see sheet normality. If the p-value for this normality check was below 0.05, this would indicate lack of normality. Since it is 0.983, well above 0.05, it passes the test. We want to check that the process has not significantly changed during the time of our experiments, see sheet trends. No out-of-control alerts appear in this SPC chart of the residuals, so there is no evidence of significant process changes. Notice that we have a timestamp next to each residual. That would be the timestamp of the moment each experiment was performed. It is essential to collect these timestamps to investigate any anomalies detected during the analysis. Conclusions. Design of experiments, DOE, is a powerful methodology for process improvement. It enables the identification of critical process factors based on data rather than impressions. We can estimate the optimal values of these critical factors to optimize the process. Excel provides some useful data analysis tools to achieve this. Some processes' outputs don't have a linear relation with the critical factors. In this case, we will need a more sophisticated formula such as response surface DOE. You can see this article in Polyhedrica blogspot.